Hi, so I want to make a little introduction for you to algebraic geometry. It will be a very informal one because of the notation I'm going to use. So what's algebraic geometry? On one side, we have algebra, and on the other side, we have geometry. So to me, algebra is like the heart of mathematics. Why? Because you only need to take a set. For example, here I took the set G equal to 1, 2, 3, 4, and then you have to associate to that operation. And so this operation is just a map that takes two elements of this set G and associates to that, in this case, for example, the product of them. And if you put other properties, if you put 4 properties to this set G, for example, associative or other properties, you can call this structure a group. So a group is a set plus an operation that satisfies some properties, and that's called a group. And that's everything. So I'm not going to state the properties here. It's just a very informal introduction. And then you can do some stuff with this, a lot of stuff, and you can also read books about this. Abstract algebra is a very, very big branch of math. And for example, some mathematician said, oh, look, some elements, or maybe all elements of these groups commute. That means A times B is equal B times A. So if all the elements of this set commutes, then we are going to call this set an abelian group. And then other mathematicians said, oh, look, I have a group, I have a set G, such that all the elements there don't commute. And they called this set a not abelian group. And also there is a branch of math called non-commutative algebra or not abelian algebra, and it's another big area of math, and it's very hard to work on that because nothing commutes there. And then there is geometry, and geometry is the study of the shapes. And then we have algebraic geometry. So algebraic geometry started back with the Greeks. And an example of that is the Pythagorean theorem. I think you've heard about it. So in the algebra side, people were asking each other, so if we have x squared plus y squared equals z squared, what are the values x, y, and z that satisfy this equation? And then started working with algebra. So with algebra we can do, okay, z squared is equal to, z is equal to the square root of x squared plus y squared is also equal to minus the square root of x squared plus y squared. And then you can multiply all of this by 2, for example, and so on. So all of this is algebra. And on the geometric side, there were some guys that were saying, oh, look, I have a vector that has a modulus of 3, and I have another vector that has a modulus of 4, and we can find another vector that has a modulus of 5. And they were saying, oh, see, if we take these numbers, they satisfy this equation. So then they said, oh, if we have two vectors that are perpendicular, then they will satisfy this equation. We will be able to find another number that satisfies this equation. So they say to the algebra guys, oh, look, we found some solutions for your equation. with the help of geometry, we are looking at triangles, at the square triangles, and that's how algebraic geometry was born. Algebraic geometry was using the techniques of algebra and at the same time of the geometry to find solutions for some mathematical problems. So, in other words, what's algebraic geometry? So, algebraic geometry is the study of the zeros of a set of polynomials. So, what do I want to say with this? So, I'm going to state some definitions. So, we are going to have some polynomials, for example, f and g and h and so on. And we are going to consider the set of all of these polynomials. And we are going to call it S. In algebraic geometry, people like to call this set S for some reason. I don't know why. So this set S will contain all of these polynomials. F, G, H, M, N, and so on. For example, we can take the set S of the polynomials f and g, where f is x squared plus y squared plus z squared minus 1, and g is x plus y plus z. And now we are going to define the most important thing of algebraic geometry, that is an algebraic variety. And they denote this by B of S. So what is an algebraic variety? Is the set of all points where every polynomial in S vanishes. So how do we define this formally? So V of S will be equal to all the points where these polynomials are equal to 0. So for example, in our case, we have our set S, that is the polynomial f and the polynomial g. So for this S, B of S, the algebraic variety, will be equal to all the points x, y, and z where f is equal to 0 and g is equal to 0. So that will be equal to the set x, y, and z such that x squared plus y squared plus z squared minus 1 is equal to 0, and x plus y plus z is equal to 0. So on the geometry side, we have that this is a sphere of radius 1, and if we combine this with this equation x plus y plus z equal to 0, we are going to find that the points that satisfy these two equations are in this little circle here. So algebraic geometry is the study of algebraic varieties, and we use the techniques of geometry, and we also use the techniques of algebra, and we are now able to find solutions, and some problems are going to be easier using algebra and also geometry. And algebraic geometry is a very big branch of math. It relates to code theory, it relates to artificial intelligence, it relates to algebraic topology, to complex geometry. It also has a lot of applications to physics. And one little part of this, but a very important one, is the Riemann-Roch theorem. So we are going to study here the Riemann-Roch theorem on curves, because there is also the Riemann-Roch theorem on vector bundles, on surfaces, and other stuff too. And so we are only going to focus on curves. So I'm also going to explain you a little bit what about this theorem is. So imagine that we have a curve. Here we have a curve x, and we have some points on the curve, p1, p2, p3. So we can define a function on a curve. And a function on a curve is just a function that takes some points in the curve and associates to that some number. So in this case, I've choose x3 over y3. And we can also define a rational function on a curve. So a rational function is just a ratio of polynomials on a curve. So for example, qs over ps, where q and s are functions on a curve. And we can also define the pole of a rational function. So the pole of a rational function are all the values s where p of s is equal to 0. In other words, where the denominator is equal to 0, or where this function is not defined. So the question is this one. What is the dimension of the space of rational functions on a curve x that have poles of order at most ai at the points pi? So I don't know if you know what is a pole, but I'm going to recall what is the order of a pole. So for example, in this case, if we have our rational function that goes from a curve to some field k, and we take the point p3, x3, y3, and we associate to that x3 over y3 squared, then a pole of this function will be y3 equal to 0, because y3 equal to 0 will make the denominator be 0. So the order of this pole will be 2. So this number here is the order of the pole. So the question here is asking us, what, for example, for this case will be, what is the dimension of the space of rational functions on the curve x that have poles of order at most 2 at the points, for example, p3 and p2. So this was the question, and the Riemann-Roch theorem answers this question. So the Riemann-Roch theorem will tell us what is the dimension of this space. So this is very important for mathematicians, because a lot of them work on finding what are the solutions, what are the zeros of a system of polynomials, or what are the poles of a system of polynomials where this function is not defined. Those are the poles. And to know how many functions have poles of certain order, it's very important. So Riemann, that is a very good mathematician, he was trying to answer this question, but he only found an inequality. He said, oh, the dimension of this space is less or equal than something. And then Roch came. He was a student of Riemann, and he said, oh, if you add something here, then you have an equality. So he said, okay, so the dimension of this space is equal to the stuff you found minus the stuff I found. And so these both people, Riemann and Roch, were very brilliant mathematicians for their time. And this theorem also was very important, and it's still very important to understand and study many areas of math. So I think this will help you a lot if you want to do some research in the future, and also this will help you to know very basic concepts of algebraic geometry. And it's also a very ambitious project. So I hope you like it, and please let me know of anything if I can help you on something.